Good day, everyone. Welcome to day 2 of this lesson on introducing the basic differentiation rules. We're starting to discover that certain types of functions follow certain patterns when it comes to finding their derivatives and slopes. And today we're going to continue and we're going to introduce or talk about how to demonstrate what the derivative of two trigonometric functions, the sine and cosine function, and the basic exponential function. So we're going to learn, in the context of this lesson, we're going to learn the derivative of the sine function. We're going to learn the derivative of the cosine function. And we're going to learn the derivative of the exponential function e to the x. If you got your green paper, which is where you're recording these derivatives, this is going to be box number 3, 4, and 9 today. And we'll, at the end, maybe take a look again at some other interesting little problems you can solve once you know some differentiation rules. So it's objective number 2 and 3 today on this e-learning day. The warm-up task that's going to help us prove one of our derivatives in a little bit is this limit right here. I encourage you to pause this video right now and just take your calculator and with a table or by graphing this expression, I want you to decide what you think this limit is equal to. Notice you can't solve this limit directly because if you allow x to be 0, this would become e to the 0, which would be 1. 1 minus 1 is 0. And then x is approaching 0 downstairs too. So this is approaching 0 over 0. I encourage you to pause the video now, take a look at either a table or a graph of this expression, and look at what happens when the x value gets really, really small. Okay, I hope you tried that, and I hope you discovered that this limit is equal to 1. In a minute, this will be helpful in proving one of our derivatives today. Let's first take a look at two trigonometric functions, sine x and cosine x. What I've got on the screen right now is the graph of sine x. This is the graph of y equals sine x, or f of x equals sine x. And I'd like to take a look at this just by examining the graph at various points and either exactly or guessing what the slope of a tangent line would be. I think on the part of the graph you're seeing now, there's two places where you can already tell exactly what the slope is. If you don't know which ones I'm talking about this top of the hill right here, because this is smoothly turning, and at the very top, the tangent line would be horizontal. In the same way, right here, the tangent line is horizontal. Now, I numbered my scales by ones, so it's it'll be more convenient for other purposes in a minute, but if we were graphing a trig function, normally we would mark this scale off by things like pi over 2s or pi over 3s or pi over 6s. So you probably already know that the top of this hill here really corresponds to the value pi over 2. And the slope at that point appears like it's 0, so what I'm going to do with my red pen is draw a dot corresponding to this value of x, but I'm going to mark it with the height corresponding to what the slope is. And the slope of this is 0, so I'm going to mark with the red pen you know what, I'm going to use blue since I'm using red for the tangent lines. So I'm going to draw with the blue pen a dot whose height is what the slope of the red line is. Which means right here as well, which by the way, this would correspond to 3 pi over 2, and that is right, also having a slope of 0. There is two other points that I think I can tell about what the slope is. Again, I'll grab the red pen. Look back here at 0. If you imagine a red line being tangent to this curve, if I extend it up further, doesn't it look like it's approaching the point 1, 1? Which would mean the slope of this line is 1. And so with the blue pen, I'm going to mark a dot on x equals 0 that has a height of 1. In the same way, it looks like if I were to draw a tangent line right here, which by the way, this is pi, x equals pi, it looks like it has the exact opposite slope. It looks like it's going about down 1 over 1. In fact, it is going down 1 over 1. So here at that value of x, at pi, the slope is negative 1. And I think it's going to do the same thing at 0 as it does here at this point, which by the way is it's a little bit past 6, and that's the end of that first cycle, which is 2 pi. It looks like the slope is the same as it is back here at 0. I would say it's going to be 1. So here at 2 pi, slope's 1. So now imagine connecting the dots. This graph is smoothly rising and falling. The slopes are smoothly going to be changing. So I'm going to be able to draw a smoothly drawn curve between all these points. And I'm hoping you're going to recognize what I'm drawing here is this. Looks like I can extend this further here. Now I want you to look at just the blue. It starts at 0, 1, gradually decreases until it's got a value of 0, because that's what the slope of the green graph was. At pi over 2, we have 0. At pi, the slope of the green graph was minus 1. At 3 pi over 2, 0. And then at 2 pi, 1. I hope you recognize what we just plotted here is the cosine function. So what we've discovered here, kind of intuitively, okay, it doesn't really make, this isn't really a proof, but it appears very looks pretty convincing that the slopes of the sine function are measured by the cosine function. Indeed, that's what it is. So the derivative of sine x, I'll just write it out fully here, the derivative, or in other words, the way you measure the slope of a sine function is with the cosine function. So this rule would go on your green sheet in box number 3. The derivative of sine x is cosine x. And let's try it again. This time I'm starting with cosine graph, and we're going to map out the slopes of this graph. So in the same way, I have a number of places where the slope is 0. And by the way, those are at 0. This corresponds to pi. This corresponds to 2 pi. Right? And so I'm going to use the blue pen again here. And whatever the slope of the red tangent line is, my blue dot will have that height. So 0, 0, 0. Just like with the sine curve, when it's crossing the x-axis, it's going to have a slope of either minus 1 right here or 1 here. These points end up having a slope of 1. And so I'm going to mark at this spot a height of minus 1, because that's what the slope is. And here, 1. By the way, these correspond to pi over 2 and 3 pi over 2 on the x scale. Okay, now watch as we connect the dots. Smoothly connect the dots. Now after the last demonstration, maybe you were predicting that the derivative of cosine would be sine. Looking carefully though, it's not quite that, because it looks like, if you go back to the previous screen or just remember what the sine function looks like, it starts at 0 but it goes up first and then down second. What I just drew is a very similar curve, but it's going down first, then up second. It's doing the exact reverse of what I would expect the sine curve to do. So in fact, it's not the sine function, but it's the negative of the sine function, and so that's what this is. The derivative of the cosine. In other words, the slopes of the cosine function are measured with the opposite of the sine function. This would go in your green paper under box number 4. And let's just fill them both in on this screen here now. The derivative of sine of x, in other words, the slopes of the sine function are measured by the cosine function. And the slopes of the cosine function are measured by the opposite of the sine function. So combine that with some other techniques you've learned now. I can now find the derivative of a combination of these rather quickly. All I've done is I've taken a cosine function and multiplied it by 3. I've taken the sine function and multiplied it by 5, and then I'm adding them together, and now I'm calling that my f of x. And now I'd want to know maybe the slope rule for this function, the derivative of this function. Well, we have a constant multiple rule and we have an addition rule. The constant multiple rule says if I know the derivative of cosine x, then the derivative of 3 cosine x is going to be 3 times the derivative of cosine x. And if I know the derivative of sine x, the derivative of 5 sine x will be 5 times the derivative of sine x. And we would likely then just clean this up by multiplying this together and probably writing negative 3 sine x plus 5 cosine x. And that's perfectly fine. If you really like to have the positive terms in the front, you could rewrite it one more time as 5 cosine x minus 3 sine x. But the way I've got it is perfectly fine. All right, I'd like to talk about the derivative of this exponential function next. And this time I am going to actually do a proof, write through a proof of this without looking at the graph. So I am actually going to go back here and use our definition of a derivative here. That definition, remember, was to take the limit as h approached 0, f of x plus h minus f of x over h. I'm going to try and apply that to this function. Okay, so I'm going to take the limit as h approaches 0. Now this time f of x plus h is going to be e to the power of x plus h minus f of x, so minus e to the x, and it's all over h. Notice again, I can't evaluate this limit directly because it would approach e to the x plus 0, e to the x minus e to the x over 0. But there's some handy algebra that will solve the limit for us with the help of the warm-up problem today. Look at this upper left corner. I want you to first agree that that could be written e to the x times e to the h. Because remember your exponent properties, when I multiply with the same base, these exponents actually add. And I had them adding up there, so I can technically write it this way. And then just subtract the e to the x again, and it's still over h. Now this still yields 0 over 0, but now it is clearer that I can factor the numerator because there's a common factor of e to the x, which would leave e to the h minus 1 over h. And then I would take the limit as h approaches 0. Now I'm going to cleverly rewrite this one more time by kind of rewriting this large expression as this. E to the x over 1. Just kind of separate that. And then I've got this other fraction here, e to the h minus 1 over h. And now take a quick look at that second guy right there. When the limit as h is approaching 0, if you look at that and compare it to the warm-up problem, it's the exact same limit. The only thing we changed was the name of the variable. In the warm-up problem, we had e to the x minus 1 over x, and x was approaching 0. This is e to the h minus 1 over h, and h is approaching 0. So in either case, that limit is going to be 1, which makes my overall limit e to the x over 1 times 1. The overall limit then is just e to the x. Okay, this is the time to get excited. Look at this. The derivative of e to the x was e to the x. the derivative of e to the x is e to the x. This function is its own derivative, guys. There's nothing to memorize. This is my favorite derivative because e to the x, its derivative is itself. There's nothing to change. It's just left alone. If you think about it, that means if you were on the graph of that exponential function, okay, remember the shape looks like this. What that proves is no matter what point you are on, okay, if I pick some x and the y coordinate then would be e to the x, guys, the slope of that graph is the identical value of the y coordinate of the point, because the derivative of the function is the function value, is what this proves. The derivative or slope of the e to the x function is the same as the y value of the point. That's the only function that does that. Okay, so this can go in your green sheet under rule number 9. The derivative of e to the x is e to the x. And now I've got a function here where I've got the last 3 derivative rules we've learned today. If I would like the derivative of the function 5 sine x minus 3 cosine x plus 8 e to the x, I'll just apply the sum and difference rule, the constant multiple rule, and the 3 derivative rules we've already learned. So the derivative of 5 sine x would be 5 times the derivative of sine x, 5 cosine x. Now be careful, I've got minus 3, but the derivative of cosine is negative sine x. And this is my favorite one, the derivative of 8 e to the x will be 8 times the derivative of e to the x, but that is just itself. So the only thing to be careful of here is this double negative. So my final derivative expression will be 5 cosine x plus 3 sine x plus 8 e to the x. That is the derivative of my given function. There will be a video coming up next. We'll save this for another video where we look at some of the other examples on these slides and lessons. Okay? We'll see you back for video number 2 in a few minutes.